Thank you.
Thank you very much for Dr. Chowdhury's very kind introduction. I'm very humble and fortunate to have this opportunity to present some of the recent work we have been doing related with rural engineering and connected community. So also I'm here to share the opinion and share the development. If you have any questions, feel free to know at any time. Okay. So a little bit more introduction about myself. Okay. So as you can see, this is my background. I get my bachelor degree. I have 2 bachelor degrees in structural engineering and construction management. One from Huazhong University of Science and Technology, the other one from Wuhan University. Then I moved to University of Kansas, get my first master's. Then I get the second master's in theoretical applied mechanics. Finally, a PhD degree from UOPA in 2014. By the way, PhD stands for permanent head damage. One is enough. The rest is you can get more. Yeah. So you can see my hobby is to collect the diplomas. Yeah. All right. Today, I hope to use this 1 hour, approximately 1 hour slot to introduce some of the railroad stuff. It's actually very important for us. Some of the intelligent track inspection technology we have been developing over the years. And at the end, I will introduce some of the connected community and some of the technology we have been working on. Hopefully, we can improve the life of the community. Okay. So a lot of people are not aware of how important the U.S. railroad is. So some of the facts listed here is actually the largest railroad network in the world, with about like 260,000 kilometers long. Guess which one has the second largest? China. Guess how big it is? Only 150,000 kilometers. So U.S. has the way more the largest network in the world. And you probably know a lot of the freight is transported by the semi-trucks, but actually 40% of the freight is transported by the railroad. Think about the car manufacturers in Spartanburg, in Charleston. Those cars actually transported by the railroad first, then transported by the semi-trucks, the last mile to the dealership. Okay, and the U.S. has the most efficient railroad network in the world. So I know nowadays people are talking about like electric vehicles and high efficient automobiles. So I don't know which one you drive. So let's think about like Honda or Toyota, right? Those are the most efficient cars we have. So typically they advertise with this can reach 33 miles per gallon, something like that. Well, how efficient is the railroad? So back to 10 years ago, even 15 years ago, one cup of diesel engine fuel can transport 142 miles or 1 ton of freight for the U.S. railroad. That's how efficient it can be 10 years ago. And let alone how efficient it can get nowadays. It's really important components of the transportation network. Okay, so a little bit basics. What is track? What is track? In your mind, probably the first image you have is this is the track. Yeah, we are close to the stadium, of course. So what is track? A track is a guided way. It's guided. You cannot cross the different way. Okay? You have to stay on your track. Similarly, we have the railroad track. It's a guided way. We do not maneuver the directions, but only way to control is the speed along the track. So in case you miss the news, there was an accident in Ohio in February. So this is kind of like attention for us we have to give for the railroad. This is actually related with our life. It's very important. It's related with safety, with efficiency, with transportation costs. So it's an important system. We have to inspect and make sure it can be operate safely. So we have to do a lot of regular inspections. So FRA actually require each track segment to be inspected at least once every 2 weeks. It's actually very frequent compared with the network it actually has. So a lot of traditional ways you can see we use the rulers to measure the gauge. Okay, we try to see whether the bolts are well maintained or not. Okay, sometimes we check the switch point and crossings, and we also have some like hand push cars to measure the different components of the tracks. Okay. So another hot technology recently is the computer vision and you probably already heard that because you guys are working on the autonomous vehicles. So we want to make this technology work for different disciplines. So why not we can make it work for the railroad inspections? Would that be helpful or not? What is computer vision? And so what is definition of computer vision? You may have your own definition according to University of Wikipedia, which is the most cited source. This is the definition. Okay? A lot of definition in that website may not be the truth, but this one they actually copied from IBM's definition. So this is tells us basically what it tells us is we try to mimic the way our human brain process the image we can get. Okay? How we get image from our eyes and how our brain process. Okay? Basically, that's computer vision. So if we see something, we will know something. If we can let the computer see something, we hopefully can let the computer know something. Okay, so that's the idea. Okay. How many of you use a camera? You use a smartphone before? You all use smartphones? Have you ever taken a selfie before? Yeah, right. Everybody did. Otherwise, you are not belong to this generation. Okay. So whenever you take a selfie, you can see there's a box outlining your face. Those are called bounding box. So which means the chip can actually know where our human face is. Right. So if you try to fool the camera, you can draw a cat or a dog. It will not detect because the model is not trained for that. Okay. So that tells us we cannot fool the camera. So the camera actually know which one is a human face, which one is not. Okay. Even they are similar. Okay. Those are the detected faces. So if we can train a camera to detect human, we can train the camera to know what are the different components that are used in a railroad track. We can do the same thing, right? Okay. And we try to do something else. Of course, there are a lot of generalized models we train to detect anything you want. Okay, detect the cops, detect the vehicles, detect the cats, detect the even settler, anything you want. Okay, we can do the same thing. Yeah. Okay. The only drawback is we have to provide enough data. We have to collect enough images to train, okay? And that will take time and take some effort. Help us. Okay. So one more interesting question I want to ask you before we come to the cream of the presentation. Have you ever been asked the question, you be a robot or not? You did, right? You probably look at something like this, right? Ask you to see where is the traffic light, which one is not. You did that, right? Okay. Or a different type of question would be to spell it. You didn't realize it. It's actually also the training process. So Google actually used free labor from you to train their engine. They just never paid us. So we all contribute to this technology development and perfection. Okay. So then the natural question is, since the technology is, why not we apply to the railway inspection? Okay. You have the railroad to make sure the track is safe. Okay. But a lot of those generalized models, they are developed for generalized detection. They are not developed for specific detection purpose, which means it may be able to detect a lot of different things, but for the specific object, the accuracy may not be there. Okay, so this is what we try to improve. Okay, if you look at the railroad track, okay, there are a lot of different challenges. First of all, the background and the foreground looks fairly similar. Okay, it's just a brown. Okay, there's a lot of useful features there, and also the different components look very similar. Okay, and another problem is we do have this very long rail, but sometimes we also have very tiny spikes like this stuff. They're very tiny. So in terms of computer vision detection, the scale is quite different. Okay, it's kind of like if we have a person that have like a short sight, they cannot see very far very well. Similar like the computer model. If it was trained to detect the bigger things, they will have insufficient accuracy when detect the small things. And also, sometimes we cannot control when we have the opportunity to go to the track to do the inspection, right? It really depends on the track hours we can get. Sometimes it is bright, sometimes it gets really dark. Okay. How we can help the model to understand what is a component in a dark environment is also another challenge. Okay. And even early in the morning or in the sun, very sunny day, okay, we may have the light brightness imbalance issues. One side of the rail could be very bright with direct sunlight. The other side could be very dark. Okay. Those imbalance issues will also cause problems. Okay. So this is what we try to solve. All right. Okay. Just keep in mind those are the challenges. Okay. Then I'll introduce you what we have been done with these topics. Okay. Okay. An example of this is a typical track component. We do have the spikes, we have the clips, we have the rails. Okay, so I'm going to show you what we can do. this is a video that we can process the images through a smartphone. Okay, so you can see my student was walking along the track. Of course, you saw the images previously. Nobody gonna paint all the spikes red and clips green. There's a lot of paint. So basically, our computer vision model is actually when it receives the image, it will assign the mask and outline the contour of the component. That will help us to know whether the component is missing, whether the component is broken, and to what degree. Okay, and just to illustrate the performance, this images shows you the original image at different light conditions, from the original image all the way to the 70% reduction of light. Okay, if I enlarge it, you can see it's even difficult for myself to see any component. It's very challenging, right? Can you count how many spikes you have there? Very difficult. Okay, let's see how about the model's performance. So these two are different models we developed with different backbones. Okay, one is with 101 layers, the other one with 50 layers. You can see the performance. Even with this image, it's hard for us to detect all the components, clips and spikes. The computer model will be able to detect it to a fairly accurate value. Okay. Those are the accuracy to the detection performance. Accuracy with the two different backbone we use. To compare that with other state-of-art models, those are the performance with other models that are popular in the computer science department. And you can see for the specific railway track detection purpose, our model has a higher accuracy compared with other state-of-art models. Okay, that is because we tailor it and customize it for the specific application. Okay. All right, and also another contribution for this study is it's the first time to reach a 30 frames per second with a single GPU. What does that mean? So think about when you take a video with your smartphones. The typically frame rate is 30 frames, okay, which means we take 30 images per second. If our processing time is equal or bigger than that, which means we do not need to store any images at all. So we do not need to waste our storage space while we can directly process them and just record the information. Okay, this is why it's real time. And we're very proud of it. So this was published in the Computer-Aided Infrastructure Engineering Journal. We have 7 reviewers, and none of them agreed at the first time they saw this strong statement, but eventually we can. Okay, so how do we achieve it? So this is our computer vision architecture and our backbone used. Okay. So if you are interested in the details, feel free to let me know, and I'll be willing to share the stuff. Okay. All right. So talking about the model could be very abstract. Let's just take a step back. Okay. Take a small question. Which one will you pick? I have different cars. Which one will you pick? Come on, guys. Don't be shy. Just pick one. There's no right or wrong. Mustang. Right. Okay. Anything else?
The Rolls Royce.
Rolls Royce. Great. Great taste. Okay. But in order to help us to make a decision, we need to know why we are picking this car for, right? What is motivation? So if you're going to buy a batch of mulch or sand, you probably won't pick the Rolls Royce. Gonna ruin the car, right? You probably pick a pickup truck. But if you try to haul a group of students to attend a conference, you probably will not pick up a master. You probably pick a van, right? It really depends on the purpose. So when you think about when you pick up something, it really depends on the need. If you want to have a race, yes, you will pick the master, right? You can even customize it to let it better suit your need. With better engine, with better intake, with better tires, you customize. So this is actually exactly the way we do the development. Okay, so we took the generalized model, we find what is the most suitable for our application need. We find that, then we customize the model by revising and or the model. If the model is not available, we start to develop our own architecture. So this is the philosophy behind. Okay, good. All right. So one example of this is the activation function. If you are familiar with computer vision model, activation function is a function to determine whether each specific neuron can be activated or not, or whether it's needed to be activated or not. Okay, so we develop a hybrid activation function and compare with the other state-of-art activation function. In that case, when the neuron is needed, it will be activated. When the neuron is not needed, it does not need to be activated. So in this way, we can do two things. One is to save the computational resource. The second one is if we do have a insufficient computational resource, it will accelerate inference speed. Okay, so if you still remember previously we reached 30 frames per second. So this is the second generation model we have. This is based on the Euro-V4 hybrid, our hybrid activation function. It can reach almost 80 frames per second, which means if we have a camera can take 80 pictures per second, we can process it without storing any particular frame. Okay. So the rest are the different state-of-art models back to the time we published it. Nowadays we have Euro-V5, V6, V7. Okay. All right. So what does those inference time mean, right? I said 80 frames per second. What does it exactly mean to the real-world engineering? Okay. So think about, we can process 80 images per second, all right? If each image can cover about 2 feet long of the railroad track, okay, then every second we can process about 160 feet long. Then that equivalent to about 110 miles per hour, which means this system can be mounted to an inspection vehicle that be able to travel up to 110 miles per hour. So this is compatible with the current FRA autonomous inspection vehicle that is the highest speed, 110 miles per hour. If it installed in a high rail inspection vehicle, it can handle the data. So that's the meaning of it. All right. So this here is some performance. So you can see the last one is the Euro-V4 hybrid, which we developed. The rest are different models. Okay. Whenever you see a red arrow, that means a misdetection. Okay. So our model detects all the components and including the rails. Okay. So then we present this result to Federal Railway Administration, and they said, well, yes, you can detect everything. Yeah. But that doesn't mean anything to us. So what we are interested in is whether there's any change over time. Okay. So the missing one clip here, missing one component there, doesn't mean there's a derailment. But we are more interested in over the time, how many actually missed. Okay. Maybe this April we have 5, but next October we find we have 50. Then that raises a red flag. We are more interested in what has been changed from the previous status. Okay. So this is what we do. So this is the original image. Okay. We detect all the components. And then the next picture is actually we make some change to the track. Okay. So the first row you see, instead of the spike, we pull the spike out, just to place the aggregate. It looks like still like a spike ahead, but the model is able to tell this is not a spike. This is a stone. At least it's not a spike. So in this case, there's a missing spike. So the second one, you can see we actually install an actual spike at this location. Okay, the model is able to tell, okay, there's another actual spike has been installed. The last one, this clip, we cannot pull the clip against the regulation. So we use some aggregate and leaves to cover that. So the model is able to tell that clip is not it. Okay, so this actually helps us to report a status change instead of an absolute number. Okay, so this will help the inspectors to make a decision in the future. Okay, so far so good. Any questions? Okay. All right. So you can see this model is focused on the missing component, especially spikes and the clips. So what about the rails, right? All the trains is running on surface of the rails. So how about we do something for the rails? We did extra work on the rail surface defect. Okay, so you can see a lot of rails have those surface defects. It really depends on how big it is and what is the percentage in terms of area. We developed another model. Okay, not only be able to focus on this direction, but any arbitrary direction will be able to locate where that defect is and what is the area. If it is significantly big, we can also outline the different contour of that shape. Now we can do a summation of all the defect area and compare with the total real surface area. So that is an indicator of how good the quality of the running surface is. That will also help the railway to manage when is another time to do the surface resurface. Okay. Okay. And we got a question from FRA. Previous development is good, but how can we make it more practical? Can we develop a real system that is deployable? Okay, so that's a question. Let's have a try. Okay. So how can we do that? So we start to train the different models. Then we realize maybe for the field development, we do not need a sophisticated, right? Because if a model is able to detect a lot of general things, when we use that model to detect a specific thing, we are wasting the capability of that model. We want each model to be very, very small and to very, very specialized. It doesn't need to be able to do any other things. So similarly, we train a trainee for a specialized job. So in that case, we can reduce the model size and the parameter we need to use for the computation. So this is the result. Okay. So compare with the other small model like the Euro-Tiny, Euro-Report, Novo, you can see our model is only about 5.1 megabytes. Okay. And we only have about 1.5 gigs of parameters. So compare with the generalized model, it's very, very small. So it's a pack. So in this case, we can load it into edge computing devices. It can be loaded into your phone. It can be loaded to a $20 chip. Yeah. Okay. So we did that. So this is our first generation of field system. So we have a computing board, which is NVIDIA TX2. Okay. So this box is put in a high-tech converse sneak shoebox for maximize the ventilation and heat transfer. That was the joke. So you can see how big it is. Everything is powered by battery. Of course, at the earliest stage, we cannot afford to take everything to the field and then request the track time. So what we do is we can fold the system. I take a video in the track, and then we use a $20 webcam just to broadcast it to mimic the true scenario in the field. To let this one broadcast the video, and then you can see the model start to input all the different components. So this actually helps us to validate the model is working. Okay, so we are confident to take it for a few tests. Okay, so that is for the first validation. Then we have the second generation, which I will show. This is the actual video clip from the TCRS image collected by FRI from their autonomous vehicle. So you can see this is our inference speed. So frame per second is around like average is over 40 frames per second. You can see 1 type, 2 type, typically 3 types. Okay, and this can cover about like 48 inches each image. So this is equivalent to approximately 110 miles per hour. Okay, so we only need that shoebox, but sometimes we don't. And a computing board and a very cheap webcam to fulfill the inspection. So we do not need any inspectors to use a lot of their time to manually count how many spikes and how many clips we have in the track. If we do the same scanning at the same segment twice, we will be able to count how many are changed. We have an extra component, we have missing component, like that. Okay. Okay. So then we got another challenge from FRA. Okay. So the railroad is a legacy system. Some of them may be built back to like 18th century. Some that was built in 19th century, 20th century. The component they used in different track segments are quite different. So in the training process, it's impossible for us to cover all the different, right? Because there are so many suppliers, so many different segments. So would we be able to also detect the component that not covered in training? Would that be possible? So the model never saw those components before. We do that. Let's look at the images we have. Okay, so we have concrete ties with this type of fast clip. We have E-clip. We have different like components, right? And this uses spikes. They are all different. What if we only have one in the training data set? The rest of the 3 we not. Okay, that's a challenge, right? And that's what happened in the real world. Fortunately, with some literature review, we find a very nice technology. It's called image reversing search. So basically, we're all human beings, right? If I saw you, even if I don't know you, next time I saw you again, I know, yeah, that person I saw somewhere. I don't know his name, but I know I saw him somewhere, right? And so that tells us we can link the same image even without knowing the details about it. We can make a match. Okay, this is exactly what we did. If a person is already in the data set, okay, we can classify that person into that group. If a person is not in the data set, we can create a new group. Okay, so basically, the model need to be able to accommodate dynamic group changing. Okay, if we have new groups, we just keep forming new groups. Okay, so this is just to give you an idea what is the current development with our model. So this is a very naive GUI. So you can see when it is starting for all the different track components in the field, If it recognizes it, it will classify it into a group. If it does not recognize it, it will create a new group. Okay. And at the end of it, the inspector only need to do some post-processing and see, okay, yes, it is a real new group, or no, this is not a new group, this is the same as before. Then all the associated images will be grouped back to the original group, or will be grouped as a group. And then the next time to do the same inspection, the already created new group will not need to be classified again. Okay. So we are keep enriching our data set by collecting more data from the field. Okay. So it's kind of like evolving. Okay. So far we detected everything in the same direction, right? The rails is always running in that direction, or the rails is running in this direction. Your bounding box is like this. So what about, I do have component in any arbitrary orientation, right? Think about you take your phone out. Your bounding box is always a rectangular shape and never rotate. Okay, even you try to lean yourself, the box is still upright. Okay, so sometimes that creates a problem. Okay, so this is something we developed recently. Okay, so this is a typical SNCF inspection vehicle. So you see that the window there. Okay, that window there. I write that vehicle about 2014, and then by that time, I was sitting there and look at the catenary system and count how many sparks from the catenary system. But nowadays we do not need to do that. We only need to put a camera there and take all the images, and we'll take images from all the different components. Okay, of course they are located in different arbitrary orientations. Okay, it could be upright with different degrees. So our development is to make our bounding box also be able to rotate it, accommodate the component itself. So that we develop a rotational detector. So depending on the component of interest, we can change our detector's orientation. In that case, we can detect the component more accurately. Okay. So anything else? Anything else you think that will happen? We have fixed camera, we have fixed component. Then we started to talk about a fixed camera, and then the component can be arbitrary orientation. What about our camera is moving? That is also possible, right? Okay. What about the camera is moving? So when the camera gonna move? If you can think about a real application scenario. What? Maybe the camera screw is loose, yeah. Weathering, yeah, especially when there's windy, right? When we use a UAV, it can never guarantee your camera is always in a fixed height, fixed angle to look at the track, especially when they try to accommodate the different wind from any arbitrary orientation. Okay, so we make a try so you can see the image we collect from the Columbia area. They all have different height, different focus, different angles of images. Okay. So this is the images example. You can see they actually take different height, different focus, and different clearance. Okay. Sometimes it's a bit off to the left, sometimes it's a bit off to the right. So we develop a new model because there's no available model. There's no model available at that time. So we develop our own architecture. We're probably to name it real boundary guided net. It's a new model. So you can see compared with the ground truth, the detection accuracy is actually very well. Okay. So compare with other state of art model back to last year. So a lot of those state of art model actually have misdetection or even have very low accuracy. Okay. So why we want to do this is because when we have a very good segmentation of the rail, it actually can guide UAVs, right? It's a perfect guided way. So if we can guide it, we can develop autonomous UAV system, and then just like the train can follow the track, the UAV can also follow the track through the autonomous inspection. Okay. So this is, I need to thank my collaborators of E1 from the mechanical department from the University of South Carolina. So we started having 5. Okay. Of course, we cannot afford a very expensive UAV at the beginning. So instead, we developed a robotic ground robots and let it follow the terms. Okay. We try to see whether the robot and algorithm is able to do that. And if that's possible, we can transfer every algorithm to the UAV system. Okay. And all the components is purchased from Amazon. Okay. Battery power, you can also do the same thing. Okay. Yeah. So you can see the accuracy is fairly accurate. The accuracy level is centimeters. Okay. So think about the distance between the two rails. Okay. If we want to position the UAV at the middle of it, we do have a relatively large tolerance at the centimeter level. So this technology is applicable to autonomous UAV. So this is something we start to try. Okay. We transfer the same algorithm to the UAV. Of course, this is a simulated environment. UAV is too expensive for us. So we let the UAV to position itself based on the detected image and then position itself at the center. And then once it's cruising along the center of the track, it's also finished all the component detection purpose. Okay. So we have a pending proposal with FRA. So if they allow us to keep for the development of it. The problem is not with the FRA, it's the FAA, the regulation, whether it allowed us to use a UAV to fly over the track. Some other challenges we're going to solve in the future is if we have multiple tracks, how we make a judgment that the autonomous UAV select the route. And also if there's obstacles, right, like a gate, like a tunnel, how the UAV will know that and avoid those collisions. Okay. That's something we're going to develop in the future. Okay. Any questions so far? Good. I want to make sure you guys good. All right. Then let's come to the last part of it. So far we have been talking about how we can have the railway track safety by doing better inspection. So what about the community part? Can we do something good to connect the railway infrastructure to the community? Okay. Can we serve the community? We all know railroad is very helpful, right? It transports a large amount of freight. That is the reason you get your Prime, Amazon Prime so cheap. That is why the freight is cheaper, because it's more efficient. But sometimes it could be very frustrating for the commuters, right? Imagine you're going to be late for school and you are stopped by a crossing like this. You're going to wait there. No matter what you do, you have to wait. There's no other way. Okay. So think about you are frustrated by this situation. What about the first responders get stopped by the crossing? Then the situation could be escalated very, very quickly, because when they are responding to an emergency situation, every second counts. So we ask ourselves, can we do anything for that? Or what is wrong with current system? What is the improvement needed? Okay. There are a lot of stories you can search, right? A lot of stories in the world you can search. Police car has to find another route. A firefighter has to throw the stuff over the train, and the medicator had to throw the medicine over the train. There's a lot of stories. So if we review the navigation system, what is missing? Okay. You all use Google Map. You all use Apple Map, right? When you try to find a route from your origin to your destination, okay, those navigation systems can help you find the best route. They even can provide a lot of details along the route. For example, if a crash and how long it will delay the traffic, and what is the delay estimation at different segments. Okay, whether it's the congestion situation get really easy. But have you ever realized there's any navigation system that tells you anything about the railroad? None, right? All those software cannot have the information about when a railroad crossing will be blocked or not. Okay. So this is something. Okay. So this is actually we also get help from the C2M2 center. So we try to develop a system that is be able to monitor the railway crossing area, okay, and estimate what is the traffic delay time, and we try to estimate what is the train arrival time and departure time from the crossing. Then use that to calculate what is estimated decongestion time for the first responders. Then they can use that information to better allocate their units to reach the location of emergency. Okay. So we tried this before the pandemic. We did install a system along one of the most problematic crossing rated by the first responders from the city of Columbia. Okay. We modeled that crossing. That is along the assembly street. This is where we install our system there to monitor that crossing. Okay. So we monitor both the surface traffic and also the railroad. Okay. So then the two combined will be the estimated decongestion time. So this is from the result from the surface street traffic monitoring. We do have a certain patterns for the traffic to be accumulated and discipline. Okay? If unfortunately you are stuck in the traffic, you have to wait until the front traffic gets clear until you can pass the crossing. Plus the railway occupation time, which means starting from when the train is in the crossing to it departed. So the gate comes down, the gate opens up. Okay? That total time will be the estimated delay time. Even you are the first responders, you have to wait that long in front of the crossing. Okay. So this is how the system looks like. So we integrated with the Google Map. So if we are fortunate to have CSX as our partner, so they share with us their train dispatch information. So we can use that and the GPS location and train speed to calculate for a certain crossings when is the expected arriving time of that train, when is the expected departure time of that train. So between this period, between this time, this crossing will be blocked. Okay. So if you're familiar with the traffic management system, this is a dead link. So between that period, and then it will be reopened again if it passes that time. So during that period, if we have a first responder unit need to be dispatched and not use that link to get the route. And that was the end of that project. And we talked with the 911 dispatching center at the City of Columbia. They told us, well, we are working on a very stressful situation. What we need is maybe an automatic route planning system instead of one more information, because one more information actually stress their work. Okay? It's actually make the job more difficult. Maybe we can do one more step. We directly help them to outline a new route based on the existing dispatching system. Okay. So if we already know a certain railway crossing will be blocked, maybe we can predict the following crossings when that will be blocked, when that will be cleared again. So then we will have the sequential orders. We will know each individual street when the street is able to pass the traffic, which individual crossing cannot pass the traffic. To integrate that information into the traffic management system. Okay. Then we propose the new different branches. This is the current dispatching schematic. So basically, if the 911 dispatching center receive a phone call, they would determine where is the nearest unit and send it there. So if unfortunately that unit has been blocked by a railroad, they will report back to the 911 dispatching center. Dispatching center will target the second nearest station and then send the second unit. If unfortunately the second unit also get blocked, they will call back the dispatching center with the third unit. Okay. Well, if we already consider the potential blockage of different crossings, they actually will know the confidence levels of different units they dispatch. Then they can minimize the expected time they would use. Not necessarily send the unit near the station. Maybe send the unit with the highest confidence, the shortest time to arrive at the situation. This is what we proposed. And we did a case study in Columbia. So basically, we assume there's an emergency, just a random location near USC area. We have different fire stations, and then according to the distance, we have certain priorities. This is based on the current dispatch system. But we can have different scenarios. Okay, let's give you some example. So at this particular timetable shared by CSX, we do have two trains passing through the city simultaneously. Okay? And the different trains will block the different streets at the same time. Okay? And then those are the different potential blockage link. So, but the first responder would need those important crossing to pass and to reach the destination. All right, those are the potential blockages the first responders may encounter. Okay. For example, for this particular crossing, it will be blocked from 9:03 to 9:41, so almost 40 minutes. Okay. So if the first responder blocked there, there's nothing they can do. Okay. Okay. So based on the case study, this paper will be published very soon. I can share more details with you. So by considering the potential blockage, we actually will help the first responders dispatch system to save considerable amount of time. Again, when it's the emergency situation, every second. Okay. All right. Any questions? Good. case you also missed the news. There's another accident in Texas, also in February, and the reason of it is a semi-truck blocks the crossing. Okay? The semi-truck blocks the crossing and cannot move because there's a hump here. But when the train saw it, it's too late, cannot stop. Typically, for a train to stop, it needs about like 1 or 2 miles, at least sometimes 3 miles. But when the engineer in the locomotive saw there's something in the crossing, it has to crash. There's no way they can stop the train. Okay. So when we talk with CSX, we appreciate their help. But meanwhile, we're also thinking about if there's anything we can help them. Since we already monitor the crossing area, right? We monitor traffic. Why not we can also monitor the area, and if there's any unwanted object within pedestrians, boxes, a semi-truck, maybe we can crop that image and send it back to the railroad. So they will know the information. They know the crossing will be blocked way ahead before the train actually arrives. Okay. Then they may be able to take some preventive care before the collision. Okay, let's give you another example. This vehicle also stuck at the crossing. Okay, it's too late for the train to stop. It can crash. That is probably one of the reasons some of your Amazon Prime box get delayed. Those are all Amazon Prime boxes. So don't blame the driver. Sometimes. Okay, so we don't want something like this happen, right? We want to save the life of the driver. We want all your boxes arrive to your door. So meanwhile, we also want to help some pedestrians. Okay? If they try to commit some suicidal behavior or anomalous behavior, we try to send somebody there to help. Okay? So we can further enhance our system to detect both pedestrians and any unwanted object stuck in the crossing. Okay. Basically, when you share the information back to the railroad, is a crossing okay to cross? If there's any unwanted object, we send somebody go there and check it, okay, or clear the situation. So this is model we developed just to use the foreground and background check. I'll show you a video later. So this is user technology of foreground detection and background detection and foreground segmentation. So if there's any object that does not belong to the background information, it will be cropped out. And also depend on the staying time, the heat map will be accumulated. The more reddish color indicate a higher risk. Okay. But if an object is passing the crossing with normal speed, that will not be accumulated. This helps us to raise different flags to alert different responding parties. And another question.
So you're developing the heat map based on risks, right? I determine the risk.
We are not determining the heat map based on the risk. Is the heat map help us to classify the risk? So the heat map is developed based on how long the object is within the monitored area. The higher
the duration is a
duration,
it's
exactly.
a risk factor.
Yes,
that's your measuring the risk.
Yes, yeah. So basically within the area, if it take a normal couple of seconds to pass it, risk is low. But if
that's your risk.
Staying, yeah, exactly.
So how you're classifying the risk? What are the classification patterns?
That part we don't have a very good understanding right now. Yeah. Probably need some like testing in the field and try to classify the different behavior. So this is one model we have. The other model is we try to collaborate with the psychology and the motion sensing expert. So we can assign different components to each individuals and then trace the key point movement and then to analyze the behavior of the individuals. By doing that, we do not have the data set for that, so we have to create our own data set. Of course, we did it in a safe manner. Okay? We do have students who watch for the trends. So we let the student just act like crazy. Sometimes they just lay down the track, sometimes standing up within the crossing. Of course, when there's no trends, okay, we need to do it safely. We create the training data set and train our model. So you can see, we can allocate the different key points to each individuals, and then from that motion patterns, we analyze how they behave. Let's give you an example. If a person is approaching the crossing, if it's crossing it, then it's a normal behavior. Okay? But if this individual is spending substantial amount of time, the anomaly score will increase. If it is staying there and even lower down the center of gravity, which indicates he is sitting there or laying down there, the anomaly score is very high. Okay. Then you can later on when it is standing up again and then leave this area, then the anomaly score will be low. Based on the anomaly score and the time duration, we can predict what is the associated risk. Of course, we do not have a very way to quantify the risk, but at least it will give us the different levels. Okay. And recently, we also get help from some
Warning, warning, you are staying at the dangerous area. Please leave right now.
Advertencia, advertencia. Te estás quedando en la zona peligrosa. Por favor, vete ahora mismo.
Warning, warning, you are walking along the rail track. Please leave right now.
Advertencia, advertencia.
Okay, so if you pay close attention, you notice a different alarm, right? If the person is standing there, it's different alarm. If the person is walking along the track, it's a different alarm. But if this person starts to cross the track, there's no alarm. So we got help from some expert from psychology. That tells us if you are trying to broadcast the same message, nobody thinks you're talking with them. But if you broadcast different messages, they will feel they are being monitored, then they will behave.
Yeah, so you got that, so the psychology faculty, but did you do any testing? What is more effective? So, or just opinion? Did you do any testing? That,
Not yet.
No.
Yeah, we just developed this
Just
system.
based on his like his or her
Based on the advice
opinion
from
and
our friends. Yes. So we are going to test this system in Florida in Brightway's track because they have relatively high record of trespassing issues. Okay.
Wha-
With that, I think I almost reached the end of the time. I would like to acknowledge all our sponsors and industry partners for their generous help and support to make all this happen. And I also appreciate the C2M2 for funding part of the project.
How did the National Academy of Sciences help on the project?
That's a great question. So when I give this presentation, some people ask me whether it should be National Academy of Science or is NSF. It's actually Academy of Science. The reason is they actually have a very special program. It's called the IDEA program. So every year they only solicitate 2 ideas for the entire world to award that for any safety related improvement. So fortunately, I got one, and that helped us to develop something. With that, I will thank you your time again. And,
It's actually NCHRP idea, right?
Yeah.
National Cooperative Highway Research Program idea program, right?
Yeah. So the NCHRB have idea, the real transit has idea, and also the real safety has. The one I got is real safety.
Okay, I'm a family.
Thank you.
Any questions? So we are doing similar projects for road intersections. So any question? Because I know that some of my students work on